Right. So this video is going to be for the special right triangle lesson 7.4. And we're going to use similar triangles along with the special right triangle constants of proportionality to solve for special right triangle side lengths. So these are the two theorems. The 45-45-90 is to be used with an isosceles right triangle. So the two side lengths are going to be the same, the two legs of the isosceles triangle, opposite the 45-degree angle, and then the hypotenuse is going to be those shorter legs times the square root of 2. These are the constants of proportionalities, the x root 2. We'll see how we can use those to very quickly get side lengths when we have a right isosceles triangle. The next theorem is the 30-60-90, and this is a right triangle with acute angles 30 degrees and 60 degrees. The shortest side is x. We know it's the shortest side because it's across from the smallest angle. The medium side, or the longer leg, is going to be x times the square root of 3. And the hypotenuse of this special right triangle is going to be twice the short leg. And both of these are, I'm going to provide you these theorems on a test or quiz, but these are absolutely worth memorizing. These are used a lot in future math courses for all kinds of things. So I've used these so many times in my math career. Not just in geometry too, like in calculus and beyond. All right. So here's the procedure of how we're going to use these. We're going to go through a few example problems in a moment. We're going to set up a proportion because we have similar triangles here, so corresponding side lengths are proportional. Okay, the first ratio, we're going to use two side lengths from the problem itself, from the triangle that we're given. One, either the numerator or denominator, doesn't really matter which, is going to be something we know, and one quantity is going to be the thing that we're trying to solve for. And then the second ratio, however we set the first one up, and it doesn't matter, but the second one, we're going to have the corresponding sides match up to the first ratio, and both of the quantities from the second ratio are going to be the constants of proportionality from the theorems. After we set that up, we're going to simplify the proportion as much as we can. Quick reminder, you can simplify a proportion by factoring vertically or factoring horizontally, but not factoring diagonally. And at bare minimum, every single time we can factor the x out of the second ratio. The second ratio is going to be side lengths from the constants of proportionality, and every single one of them has an x. Once we get a little practice, you probably won't even include the x. You'll probably take lots of shortcuts. Many people can actually solve special right triangles with very little, in some cases, no work at all. But set up the proportions using this procedure for the first several problems that you practice, and as you get comfortable, look for patterns, and once you are consistently getting correct answers, then maybe consider trying to make the procedure your own a little, and you can take some shortcuts. I will tell you, on assessment, I am going to look that you set the proportion up as a minimum amount of work, even if you can do this in your head. I'm sure if you can do all of this in your head, then you can spare a couple of seconds to write the proportion out. I am going to require that for work. All right, so after we simplify the proportion, there's a few things that we can do. At least take the x out. Sometimes there's even more you can do. We're going to take the cross product, and then we're going to simplify our answer. And a couple of things are going to show up from time to time. Simplifying radicals is going to show up a little bit. Rationalizing denominators is going to show up a little bit. And I know we've talked about this before, but I want to quickly review rationalizing denominators. It is not simplified to have a square root in the denominator of a fraction. So what you can do is take any fraction with a radical in the denominator and multiply that fraction by the radical denominator over itself. So this fraction of something over itself is equal to 1. You're not changing what this fraction is, you're just changing what it looks like. Now when you multiply these two denominators, root b times root b is just b. And then a times root b is root b. So I have a couple examples here. I'm going to add a couple little details. So for the first one, if I were, after I take the cross product, had like 4 divided by the square root of 2, I would multiply that by root 2 over root 2. And my new denominator, root 2 times root 2, is just the whole number 2. In the numerator, I have 4 root 2. Now, you cannot factor a whole number out with the radical number, but you can factor a whole number with the whole number. And up top, that's 4 times root 2, and in the bottom, that's 2. So we can actually factor the whole number 2 out of the whole number 4. But you cannot factor the whole number 2 out with a radical 2. So that's why I crossed this 2 out with a 4, not this 2 with a root 2. Okay, kind of went from start to finish, but let me show you a detail here. If I had 3 divided by root 6, just to rationalize the denominator, we'd multiply that by root 6 over root 6. We get 3 root 6 over the whole number 6, and now the whole number 3 can be factored out of numerator and denominator, root 6 over 2. So that's just a quick reminder on rationalizing the denominator. It is not a final simplified answer if you have a radical square root in the denominator. And that's going to happen from time to time with special right triangles. Now, it's very important that you use the angles to determine which sides correspond. I just realized I probably should have had these theorems on the examples themselves. I am going to refer to them. So put the right isosceles here, x root 2, the 45, 45, 90, and the 30, 60, 90, x, 2x, x root 3. Okay. So occasionally we're going to see a problem where the triangle is going to be oriented the same way as the theorem, but sometimes the triangles are rotated. So you definitely want to use the angles as your guide to what corresponds. All right, so in this first example, zoom in a little. Refocus. Okay, so we're going to solve for r first. It doesn't really matter, r or w. You could probably even, some of you guess that r is going to be 8, and it is. But using the process, so our first ratio has a known and unknown value from the example itself. And then the second ratio of our proportion, that's going to be 2 sides from the theorem. Okay, so this between the 45-degree angle, and we know it's 45 because the triangle sum theorem, we got 2 congruent angles, and then the other angle is 90. They have to add up to be 90, so they're both 45 each. So this angle between 45 and 90 on the theorem is x, so 8 is going to correspond to x. This angle is also between 90 and 45. That's going to correspond to x from the theorem. So there's our setup. In terms of simplification, we can factor the x's out. And now when we take the cross product, 8 times 1, 8 equals r times 1. So 8 equals r. Zoom out a little bit. Okay, to solve for w, again, go through, it doesn't actually matter which is on top, which is on the bottom. Maybe I'll put w up top. It doesn't, you're not going to have to set up the proportion once you get comfortable with these. After you do like 5 or 6 of these, you're going to definitely see a lot of patterns and a lot of the same thing happening over and over again. So you'll be able to make some shortcuts. One shortcut that I'll describe in a little later is if you are not given the shortest side, you should solve for that first, and that'll actually come up in the next example. Anyways, I'm getting ahead of myself. So w is the hypotenuse from the theorem that's going to match up to x root 2, and then 8 is the side between the right angle and 45 degrees, and that's going to match up to x. All right, so we're going to simplify by crossing or canceling the x out. And now when we take the cross product, 1 times w equals 8 times root 2, 8 root 2. And that's it. So as I was alluding to a second ago, when given the option, it's actually easiest to go ahead and solve for the short side first. As we see in the theorem, and maybe you even picked up on the last example, when you're given the shorter side, all you need to do is multiply by the rest of the constant of proportionality to get the answer. So I was given the short leg, which is like the x, and then the hypotenuse is x root 2. Well, if x equals 8, the hypotenuse is 8 root 2. So we can kind of take some shortcuts. So I'm going to solve for r first. 4 over r. Could have done r over 4. Doesn't matter. So 4 is the hypotenuse. And this is a 30, 60, 90. So the hypotenuse between the 60 and 30 is going to match up to 2x. And then r in the denominator, that's between 60 and 90. In the theorem, that's going to match up to x. So we can start by factoring the x's out. Well, that's weird. Just kind of make them look like x's. But now they're both 1s. And then we can actually factor out the 2 horizontally as well. And now cross multiply. 1 times r is r. 2 times 1 is 2. And now we have r equals 2. Okay, I instantly know that w should be 2 root 3. But let's pretend I didn't see that instantly and walk you through the setup. So we have 4 over w. Okay, 4 is the hypotenuse. That corresponds to 2x. W is the side between 90 and 30. In the theorem, between 90 and 30 corresponds to x root 3. We're going to, we'll color code this now. We're going to factor the x's out. Oh, that looks so much better. And then we're going to factor out 2 horizontally. And now when I take the cross product, 1 times w equals 2 times root 3, 2 times root 3. All right, I'm going to amp up the sophistication a little bit here. I'm giving you an example now this time where we are going to have to rationalize the denominator. And then we'll just blast through, I'll blast through these last few examples and give you a few to try in the ed puzzle. So it is more convenient. Maybe I'll put the angles in here. The short side is definitely BC. It's definitely most convenient if we set proportion up to solve for BC first. So there's my unknown side, there's my known side. We can kind of just put meters in the end here. So BC is the side that's between 90 and 60. In the theorem, between 90 and 60 is x. So BC corresponds to x. 9 in the problem is between angles 30 degrees and 90 degrees. In the theorem, between 30 degrees and 90 degrees is x root 3. So 9 is going to correspond to x root 3. And you want to avoid thinking about it in terms of like, oh, the side on the right matches up to the side on the right or the side on the bottom. You definitely want to use the angles to detect which sides correspond. So when we take the cross product here, BC times root 3 equals 1 times 9 meters. And then to solve for BC, we're going to divide both sides by the square root of 3. But this is where we have that radical in the denominator, so we've got to take care of that. So we're going to multiply 9 root 3 by root 3 over root 3. Get 9 root 3 over the whole number 3, and then we can factor the whole number 3 out of the denominator and out of 9. So BC is 3 times root 3, and that's in meters. Now I'll use BC and AB, and this is a shortcut that I was mentioning a moment ago. When you have the shortest side, which is 3 root 3, that's going to match up to x, the side between 60 and 90, between 60 and 90. And then we're looking for the hypotenuse between 30 and 90, between 30 and 60, and that's going to match up to 2x. So we just cancel those x's out, and when we take the cross product, we get AB times 1, AB, equals 2 times 3 root 3. And let's not forget that's in meters. So again, quick reminder, and then we'll blast through the last two, and I'll give you a couple to try your own. We'll set up a proportion, first ratio from the problem, 1 known, 1 unknown. Second ratio, corresponding sides from the theorem. Simplify, cross product, simplify some more. So 6 over AC, this is the 45, 45, 90. And actually, we know it's an isosceles triangle. I'll just set up one proportion and get both of these answers. But 6 is the hypotenuse. The hypotenuse from the theorem is x root 2. So 6 is on top. X root 2 goes up top. And AC is a leg. That's going to match up to x. The x's factor. Cross multiply. AC times root 2 equals 6. Divide both sides by root 2. And then rationalize the denominator. So AC equals 6 root 2 over 2. The 2's factor out. AC is 3 root 2 meters. And it's an isosceles triangle, so we'll just use that fact. All right, last one. Okay, here's where once you get comfortable, you can really start blasting through these things. This is the short side of the 30, 60, 90. The hypotenuse is twice as long, so I already know that's 20 meters. I already know that's 10 root 3 meters because the longer leg of the 30, 60, 90 is the shorter leg times root 3. And with the right isosceles, with these two sides being congruent, the 45, 45, 90, just like I had there, I'm going to take this side and divide by root 2 to get there. So definitely work that one out if you'd like. But once you get comfortable with these, you might find yourself just seeing the answers straight away. Let me just walk through the setup. Let me write the correct answer and then walk through the setup. So for BC, that's the longer leg, corresponds to x root 3. 10 is the shorter leg, corresponds to x. Factor, factor, cross multiply, BC times 1 equals 10 times root 3, 10 root 3. BD is the hypotenuse, that's 2x over the leg. Cross multiply, BD times 1 is 2 times 10, 20 in meters. And then you have to use BD because that's the only side you know. So 20 over AB, and from the 45, 45, 90 theorem, that's x root 2 over x. The x's factor out. AB root 2 equals 20. Divide by root 2. And I'll trust that you guys can see the simplification. Well, I'll just work it out real quick. 20 root 2 divided by 2, cancel, cancel, 10. Final answers are always worthy of a circle. All right, so you're going to try some of your own and lots of practice in school tomorrow. Good stuff.